Okay, so today we're going to continue our discussion of pedigree analysis. First, we're going to talk a little bit about autosomal dominant, which we didn't talk about before, and then work to our hard part about all this, which is to say, working backwards from pedigree information to infer the mode of inheritance. We've been working forward given known pedigrees to understand what genotypes we have. Working backwards is a little more difficult. So first, let's talk about autosomal dominant traits. It's equally likely to be transmitted from male to female, unlike sex-linked. Generally, the ones that we're considering are rare in the general population, so affected individuals are usually considered to be big A, little a. So this is different from a standard Mendelian cross, where you're, say, crossing heterozygotes and you can have big A, or big A, little a. In this case, we're talking about populations and rare mutations, so we're going to assume that it's any individual showing the trait is big A, little a, unless we have other information. So that's a little odd. Okay, so here's a pedigree of an autosomal dominant trait. The parent in generation 1, 1-1, has the disease, and we are assuming that he is big A, little a. And his wife, of course, is wild type or normal. Remember, the wild type allele is going to be recessive to this mutation. And indeed, he passes the trait to one of his daughter, and also one of his sons. So it's equally likely in both directions. And the affected individuals, again, are assumed to be big A, little a. Now notice it doesn't skip generations. This isn't that extensive of a pedigree, but in general, dominant traits don't skip generations. So that's usually a hallmark. So we can assign genotypes to everybody in this pedigree pretty easily. A person that does not show a trait is little a, little a. A person that does show it is big A, little a. Okay, so by contrast, sex-linked dominant, you have a few more things to consider. We know that the gene is going to be located on the X chromosome, and these are going to be dominant. Now, this is a very rare pattern, but it does happen. So we have to consider the pattern of transmission of X chromosomes in this case, that daughters of affected fathers would necessarily have it. Remember that daughters have two X's, one from mom and one from dad. Dad has only one X, and if that carries the mutation, the daughter will definitely get it. On the other hand, sons cannot inherit it from their fathers because their fathers gave them the Y. Females can be heterozygous, show the trait, and pass it to their sons and their daughters. Again, people showing the trait are assumed to be heterozygous because such traits are rather rare. Okay, so here's a pattern of sex-linked dominant, and the dominant allele is designated by the capital letter by the X chromosome on this male. His wife is got both wild-type alleles. So as we expect, he passes it to each of his daughters and none of his sons, because his daughters necessarily got his X and the mutation, and the sons necessarily cannot get his X, and so they get the Y and no mutation, and that pattern persists. So again, we can describe genotypes to people. If they're showing the trait, they have the X with the dominant allele, and if they are not showing the trait, they have the lowercase wild-type allele. And it can be either males or females. Okay, so this is a very rare pattern, but there are examples of some sex-linked dominant traits, including a form of rickets and another important disease called Rett syndrome. Often with these kinds of things, there are no homozygotes even within families, and that's because some dominant traits are actually lethal in a homozygous condition. Okay, so now we're going to start working backwards, and what we're going to do is look at some pedigrees and try to decide what the mode of inheritance is based on the pattern of transmission that we see. Okay, so there's only 4 possibilities: autosomal recessive, autosomal dominant, sex-linked recessive, and sex-linked dominant. So our approach is going to be to eliminate the others, pick out the one that must be right, the only one that can be right, by finding patterns which are inconsistent with all the other modes. And this can be horribly confusing, I know. All right, so we're going to have to infer or guess the mode of inheritance. Okay, so here's some pedigrees that sort of illustrate some of what the thinking is like. So pedigrees 1 and 2 are both recessive traits because the children in the second generation inherited it from unaffected parents. So we can see right away that this is a recessive trait. Okay, but we can also see right away, possibly, that the first pedigree cannot be sex-linked recessive, whereas the second pedigree can be sex-linked recessive. And the reason for that is if you look at the pattern of transmission, if this girl has the disease, both of her X chromosomes carry the mutation. She got one mutant from mom and one mutant from dad. Well, we can see there's an inconsistency here because her dad does not show the trait. So the sex-linked mode of transmission is impossible here because that would say the dad had to have the trait if that's true, but it's not true, so it's not sex-linked recessive. It can be autosomal recessive for sure, in which case both parents would be big A, little a, and the girl would have gotten the little a from both of her parents. Now, pedigree 2 can be sex-linked recessive because it's a boy that shows the trait. He gets his X from his mom. So if it's sex-linked recessive, mom could very well be a heterozygous carrier and pass that one X chromosome to her son. So she would be X mutant, X wild type, one X carrying the mutant form and one carrying the wild type. So there's a 50-50 chance she's going to give that to any one of her children. So this is consistent with a sex-linked recessive mode of transmission because he could very well have gotten it from his heterozygous mom if she's heterozygous. So for this, we can't decide whether it's autosomal or sex-linked because it could be either one. So I just wrote all this. You have to look in pedigree 1 versus 2, look at the X and Y and see if the pattern of transmission of X and Y is consistent or inconsistent with sex-linked recessive. So pedigree 1 cannot be sex-linked recessive because of what I just said, whereas pedigree 2 can be either autosomal or sex-linked. Okay, in that case, we're going to have a more extensive pedigree to be able to decide which is which. Okay, so looking at pedigrees 3 and 4, we're going to assume that this is a dominant trait. We'll just pretend for a minute that it is a dominant trait. And the same issues apply, whether it's possibly autosomal dominant or possibly sex-linked dominant. Now we know if it's autosomal dominant, you'll have equal numbers of males and females, and importantly, a child can inherit it from either one of their parents, whichever one has it. Okay, but then we have to consider the pattern of sex linkage or the pattern of transmission of X and Y's to decide whether something is possibly sex-linked dominant or not. So pedigree 3 can be sex-linked dominant because the girl gets one of her X's from her dad. So that's consistent. She would have one X from her mom, which is the wild type, and then she would also have the mutant X from her dad and would show the trait as she does. So this is a possible, either it's autosomal or sex-linked. You can't tell which at this point, but sex-linked is certainly possible. Now pedigree 4 is different because remember, the boy gets his Y chromosome from his dad. He doesn't get his X chromosome from his dad. So this is, the dad is showing the trait, and it could be on his X chromosome, that's possible, but he's not going to be able to transmit it to his son. So this pattern is inconsistent with sex linkage because the son got it from his father, and he can't get an X chromosome from his father. So in this case, we can't distinguish. So in pedigree 3, sex linkage is certainly possible. Not proven, but it's certainly possible. And in pedigree 4, sex linkage is not possible. Okay, so as I just said, pedigree 3 can be either sex-linked or autosomal dominant. It's consistent with both of these. Pedigree 4 cannot be sex-linked dominant, only autosomal dominant. If these are common traits, they could be hiding a recessive with normal parent hiding a recessive allele. But in any case, the pattern of transmission of the X's to the male progeny or female progeny is how you go about determining this. So the son gets the X from his mom, not his dad. So the fact that the father is transmitting it to him means it cannot be sex-linked. Okay, so here's an autosomal recessive trait. Who are the obligate carriers? Okay, so the way to look at this is, well, two ways, really. If somebody shows the trait, then they're little a. And so they will give a little a to each of their children. So any child of an affected parent will necessarily be a carrier. They have to have that one of their alleles came from their affected parent, and so that's what they have to have. The other obligate carriers have to do with anybody that has an affected child. They necessarily must have been a carrier. So, for example, in individuals 8 and 9 of generation 3, they have an affected child, and so they are necessarily both of them carriers. Okay, so there's other reasons too why 9 is a carrier, because his dad has the trait. So his dad was little a, and so the son must necessarily also have a little a, have one little a allele, even though he's phenotypically normal. So his genotype is big A little a. And there's, other ways of going through all these to see, but actually, even if 3, 8, and 9 did not have an affected child, we would already also know that they were obligate carriers, because 2, 4 has the trait, so all of his children are necessarily carriers. So there's a lot of redundant information in here. So you should be able to go through these and assign genotypes to all of the necessarily carriers, but also say that people that are not themselves necessarily carriers may or may not be heterozygous. They could be, but they're not necessarily so. Okay, so I just put little marks in the spaces of the people that are necessarily carriers. Okay, so there are actually 4 people in this pedigree only that are not carriers. One is 2-7, and the other is 3 of the 4 children in the last generation. Now, the last generation, they do have an affected sibling, because we know their parents are heterozygotes. There's not a big deal with that. But those children could be either big A, or big A, little a, depending on what alleles they got from the 2 parents. So those are possibilities for all. So we have to say with those, they could be carriers, but they're not obligate carriers. Okay, so here's a simpler way of looking at pedigrees, where you don't have to infer the mode of inheritance, but rather look at specific individuals to see what they may rule out. So this is a way of sort of extracting a little bit of information without making you look at the entire pedigree. So the question is, which of the following people in generation 3 rule out sex-linked recessive as a mode of inheritance of the trait? So the easiest way to do that is just go through, of the offered options at least, whether the pattern is consistent or inconsistent with sex linkage, recessive. Okay, so 3-2 is a male. He does not show the trait, so there's nothing inconsistent about that. It's perfectly okay. He gets his X from his mom, and so she could be a carrier, we don't know, or she could not be, but there's no information that we can really learn from this. 3-3 doesn't help us at all, because neither of his parents has a disease. 3-6, okay, he inherits the disease from his mother, and the mother, if it's sex-linked, recessive, she would have both of her X's with a mutation on it, in which case she could very well pass it to her son. So there's nothing inconsistent about that at all, so that he doesn't rule it out. Okay, 8, however, does rule it out, because she's a female, and so she has 2 X chromosomes. Now, she could have gotten 1 X chromosome mutant from her mom for sure. Well, she would have gotten it. But she would also have to get one from her dad. So the fact that dad doesn't show the trait means that he doesn't have a mutant to give her, and she's got 2 mutants for sure. So 3-8 rules out sex linkage, recessive, as a mode of inheritance of this. And 3-9 does not rule anything out at all, doesn't have the trait, not obligatory. If it were sex-linked, she could get 1 mutant X from her mom, but the fact is she gets an X from her dad also, and that would hide the recessive. So there's no contradiction there. So 3-8 is the one that rules out sex-linked recessive, because the dad should show it if it were, and he doesn't. How's that for confusing? Okay, so by the way, the answer is D, but 3-7 also rules it out. 3-7 because if it were sex-linked recessive, mom, who has the trait, would have 2 mutant X's, and her son would necessarily get 1 of those. So he rules it out, because if it were sex-linked recessive, he would show the trait, and he doesn't. Okay, in this pedigree, some of the individuals who rule out sex-linked dominant as a mode of inheritance is or are. Let's look at 2-1. All right, 2-1 inherited this trait from his father, right? And we know that he does not get his X chromosome from his father. He got his Y from his father. So this is a pattern that's inconsistent with sex-linked dominance. he can't inherit his father's X. Okay, so then 2, 1, and 2, 6. Well, kind of the reverse of that argument. The girl does not show the trait. If it were sex-linked dominant, she would have to because she gets her father's X. She would necessarily be showing the trait because she gets one X from her mom and one X from her dad, and we know that if it's a dominant trait, she would be showing it. So 2, 1, and 2, 6 is the correct answer here. Okay, to eliminate the other possibilities, 2, 5. 2, 5 is completely consistent with sex-linked dominant because the girl would get her dad's X. 3, 1, and 3, 8. 3, 1, etc. 3, 1 also would get her dad's X, so that's completely consistent. 3, 8 is consistent because her mom has it, so that's not impossible. She gets one of her mom's X's, and if it's a dominant trait, mom could be heterozygous, and so that's completely consistent with sex-linked dominant as a mode. So the answer is B, 2, 1, and 2, 6 rule out sex-linked dominant. Okay, we're talking about autosomal recessive traits. We've had many examples of these. And some of the famous sex-linked recessive traits, we've had at least some of these. And we'll go on to talking about autosomal dominant traits next time.